What if I told you that right now, at this very moment, the entire foundation of physics, everything we've built over 400 years, is beginning to crack? Not because we got it wrong, but because we've gotten so incredibly right that we've reached the edge of what reality will allow us to know. In 2022, a team at CERN measured something that shouldn't exist according to our most trusted theories. The W boson, one of the fundamental particles that carries the weak nuclear force, was heavier than it should be, not by a little. By enough that, if confirmed, it means either our standard model of particle physics, the most successful scientific theory ever created, is incomplete, or we're witnessing something even more disturbing. The universe itself has fundamental limits on what can be known. Here's what will blow your mind. We're not just approaching theoretical limits. We're approaching actual physical boundaries written into the fabric of space-time itself. There are things the universe won't let us measure, distances we can't probe, energies we can't reach, not because our technology isn't good enough, but because the laws of physics themselves say, no further. And the most terrifying part? We're starting to suspect that these limits aren't random, they're connected. String theory suggests we need energies a quadrillion times higher than the Large Hadron Collider to test it. Quantum gravity requires us to probe distances smaller than anything physically possible to measure. Dark matter refuses to interact with our detectors. It's almost as if the universe is hiding something from us deliberately. Before we dive into this rabbit hole together, smash that like button and subscribe, because what you're about to learn will fundamentally change how you see reality. And I'm curious, drop a comment telling me what country you're watching from and what time it is right now. I want to know where in the world minds are being blown as we speak. Let's build a global community of people brave enough to stare into the void with me. Now, let me take you back to understand how we got here, because the story of physics approaching its limits is really the story of physics approaching perfection, and that's exactly the problem. In 1900, Lord Kelvin, one of the greatest physicists of his era, famously said there was nothing new to discover in physics except two small clouds on the horizon. Those two clouds were the failures of classical physics to explain black-body radiation and the speed of light. Within 5 years, those small clouds had become Einstein's relativity and the birth of quantum mechanics. They didn't just add to physics, they completely revolutionized our understanding of reality. Think of it like this. Imagine you're drawing a map of an island. At first, you're filling in coastlines, mountains, rivers. There's new territory everywhere you look. That was physics from Newton through the early 20th century. But eventually, you've mapped everything. The only things left to discover are tiny details, a small rock formation here, a minor elevation change there. That's where we are now with fundamental physics. The map is essentially complete, and that terrifies physicists. Because here's the twist. Unlike map-making in physics, we can't just zoom in infinitely to find new details. The universe has built-in boundaries that prevent us from zooming in past a certain point or reaching energies beyond a certain threshold. The Planck length 1.6 times 10 to 35 meters is the smallest distance that has any physical meaning. Go smaller, and the concepts of space and distance break down entirely. It's not that we can't build microscopes powerful enough. It's that space itself becomes grainy, pixelated, meaningless below that scale. Max Planck discovered this fundamental limit in 1899, and it's been confirmed by every subsequent theory of quantum gravity. Similarly, the Planck energy about Yp billion electron volts represents the energy scale where quantum effects and gravitational effects become equally important. Above this energy, our equations literally produce nonsensical results, infinities, contradictions, breakdowns of causality. To probe physics at the Planck scale, we'd need a particle collider the size of the Milky Way galaxy. The Large Hadron Collider, humanity's most powerful machine ever built, reaches energies a quadrillion times too small. But here's what's truly mind-bending. These aren't engineering problems. These are fundamental statements about reality itself. The universe is telling us, you've gone far enough. Let me give you another example. The cosmic horizon, the edge of the observable universe, sits about 46.5 billion light years away. Beyond that boundary, space itself is expanding faster than light can travel through it. Information from beyond that horizon can never reach us, no matter how long we wait or how powerful our telescopes become. It's not hidden. It's fundamentally unknowable. The expansion of space has created a permanent information barrier. Werner Heisenberg discovered in 1927 that there's a fundamental limit to how precisely we can know certain pairs of properties simultaneously, like a particle's position and momentum. This isn't about measurement devices. It's about reality itself being inherently fuzzy at quantum scales. The universe genuinely doesn't have a definite answer to certain questions until we force it to choose by making a measurement. So we're surrounded by limits. Limits on the small, limits on the large, limits on energy, limits on knowledge itself. And for the first time in history, we're bumping up against all of them simultaneously. Here's where things get genuinely disturbing, and I need you to really sit with this because it's going to make you uncomfortable. Our standard model of particle physics works too well. It predicts particle masses, interaction strengths, decay rates, everything with absurd precision. The anomalous magnetic moment of the electron has been verified to match predictions to 11 decimal places. 11. That's like predicting the distance from New York to Los Angeles to within the width of a human hair. But perfection in physics is actually a nightmare, and here's why. Between the energy scales, we can currently probe around 1012 electron volts at the LHC and the Planck. Energy at 1019 GeV, there's a vast desert, 17 orders of magnitude, where we have no idea what's happening because we can't build machines powerful enough to look. We call it the energy desert, and it's where all the answers to our deepest questions should be hiding. String theory, if it's correct, operates at energies around 1016 GeV. Supersymmetry, which predicts partner particles for every known particle, should show effects somewhere in that range. The unification of forces, the holy grail, where electromagnetism, the weak force, and the strong force merge into a single force happens at around 1016 GeV. Dark matter particles might be hiding at various scales throughout this desert, but we can't reach those energies. Ever. Not with any conceivable technology. Here's a thought experiment. To build a collider that could reach Planck energies, you'd need to accelerate particles around a ring so large that if you tried to build it on Earth, the accelerator would collapse into a black hole under its own gravitational mass. You'd literally need to harness the entire energy output of the sun for millions of years to power a single collision. The energy required is so vast that creating it would itself create a black hole. The universe has set a trap. It dangled answers just out of reach and made it physically impossible to grab them. Nima Arkani-Hammond, one of the leading theoretical physicists at Princeton, calls this the nightmare scenario, a future where the standard model continues to work perfectly. No new particles are discovered, and we're left with a theory we know is incomplete, but can never test beyond. And here's what will blow your mind. We might already be living in that nightmare. Since the Higgs boson was discovered in 2012 completing the standard model, the LHC has found essentially nothing else. No supersymmetric particles, no extra dimensions, no dark matter, just the standard model, working exactly as predicted, giving us no clues about what lies beyond. Think of it like being given a jigsaw puzzle where you've placed 95% of the pieces, and they form a beautiful, coherent picture. But the remaining 5% of pieces are locked in a box you can't open, and without them, you can never know what the complete picture truly shows. That's where physics is right now. The precision of our theories has become our prison. Now let's talk about what might be the universe's cruelest joke of all: the incompatibility of our two most fundamental theories. General relativity, Einstein's masterpiece, describing gravity, space, and time works flawlessly at large scales. It predicts the orbit of Mercury, the bending of starlight, gravitational waves, black holes, the expansion of the universe. Every prediction has been confirmed. Quantum mechanics, the theory of the very small works with equal perfection. It predicts atomic spectra, chemical bonds, the behavior of semiconductors, the existence of antimatter. Every prediction confirmed. But when you try to combine them, everything breaks. Not fails, breaks. The mathematics produces infinities that can't be removed. The equations become meaningless. It's like discovering that the grammar rules for English and Spanish are fundamentally incompatible. You can speak one or the other, but any attempt to merge them produces gibberish. This isn't a small problem. This is physics's deepest crisis. At the event horizon of a black hole, both gravity and quantum effects become important. Our theories literally can't tell us what happens there. At the Big Bang, the entire universe was compressed to quantum scales, while gravity was infinitely strong. We have no theory that works in those conditions. None. We can trace the history of the universe back to y minus 43 seconds after the Big Bang. They plunk time, and then our equations just give up. John Wheeler, who coined the term black hole, spent the last decades of his life obsessed with this problem. He proposed that at the Planck scale, spacetime itself becomes foamy, probabilistic, chaotic, what he called quantum foam. Space and time aren't smooth, but seething with quantum fluctuations so violent that tiny black holes and wormholes pop in and out of existence. But here's the catch. We can never observe quantum foam directly. To probe those scales, you'd need to focus so much energy into such a small space that you'd create a black hole, which would immediately hide the very thing you're trying to measure behind an event horizon. The universe has literally made its deepest secrets self-concealing. String theory promises to solve this by replacing point particles with tiny vibrating strings at the Planck length. Different vibration patterns create different particles, electrons, quarks, photons, even gravitons. It elegantly unifies quantum mechanics and gravity. And this is a massive but string theory, requires 9 or 10 spatial dimensions. We observe 3. Where are the others? Curled up at the Planck scale, string theorists say, too small to ever observe directly. The theory also predicts around 10,500 possible vacuum states, different ways the universe could arrange itself, and we have no way to calculate which one we're in or why. Edward Witten, often called the smartest living physicist, has devoted his life to string theory and admits we're nowhere close to being able to test it experimentally. The theory might be true. It might be beautiful mathematics with no connection to reality. We might never know. Luke Quantum Gravity, string theory's main competitor, suggests space itself is made of tiny loops at the Planck scale quantum threads woven together. But it faces similar problems. Predictions that require Planck scale energies to test. We have mathematically sophisticated theories about quantum gravity, but the universe has placed the evidence we need in a realm we can't reach. It's like being told there's a room in your house that contains the answers to life's biggest questions, but the door is painted on the wall. It's not a real door, and there's no way through. Let me tell you about one of the most embarrassing secrets in modern physics. We don't know what 95% of the universe is made of. And as we approach the limits of physics, this ignorance is becoming more, not less, profound. In the 1970s, Vera Rubin was measuring the rotation speeds of galaxies. Basic physics says that stars far from a galaxy's center should orbit slowly, just like Pluto orbits the Sun slower than Earth does. But Rubin found something shocking. Stars at the edges of galaxies were moving just as fast as stars near the center. The galaxies should be flying apart, but they're not. The only explanation: there's invisible matter-dark matter creating additional gravity to hold galaxies together. About 5 times as much dark matter as ordinary matter. We've now confirmed this through gravitational lensing, galactic collisions, and the cosmic microwave background. Dark matter is real, but we have no idea what it is. It's not ordinary matter that's just dark. It's not black holes. It's not neutrinos. It's some completely unknown particle that interacts with nothing except through gravity. Physicists have built incredibly sensitive detectors deep underground to catch dark matter particles. But after decades of searching nothing, the universe is filled with matter we can see affecting everything around it, but which refuses to interact with us directly. Then there's dark energy, which is even weirder. In 1998, Saul Perlmutter, Brian Schmidt, and Adam Rees discovered that the expansion of the universe is accelerating. Something is pushing the universe apart with increasing strength. We call it dark energy, and it makes up about 68% of the universe. What is it? We have no idea. It looks like Einstein's cosmological constant, a uniform energy density filling all of space, but we can't calculate its value from first principles. When physicists try to calculate it using quantum field theory, they get an answer that's wrong by 120 orders of magnitude. This is called the worst prediction in the history of physics. Think of it like this. Imagine you're trying to calculate the weight of a car, and your best theory predicts it weighs either a few pounds or more than the entire observable universe. That's the level of our confusion about dark energy. Here's what will absolutely blow your mind. We live in a universe where 68% is dark energy we don't understand, 27% is dark matter we can't detect, and only 5% is the ordinary matter that makes up stars, planets, and us. Everything physics has successfully explained, atoms, light, forces, particles, accounts for just 5% of reality. We're like someone who's proud of understanding how bricks work while being completely ignorant about the 95% of the building made of something else entirely. And as we approach physics's limits, we're discovering that dark matter and dark energy might be fundamentally inaccessible to us. If dark matter only interacts gravitationally, there might be entire dark matter structures, even dark matter life, completely invisible and untouchable. Dark energy might be a property of spacetime itself that we can observe effects of, but never directly probe. The universe might be mostly made of things we're not allowed to study directly. Now we need to talk about quantum mechanics, because frankly, after a century of success, we still don't understand what it means. And the closer we look, the more reality itself seems to rebel against being understood. The famous double-slit experiment shows that particles behave like waves when not observed and like particles when measured. Electrons, photons, even large molecules exhibit this wave-particle duality. But here's the deeply unsettling part. The act of measurement itself changes what's real. Before measurement, a quantum particle doesn't have a definite position or momentum. It exists in a superposition of all possible states simultaneously. The Schrödinger equation, discovered by Erwin Schrödinger in 1926, describes this superposition perfectly. But when you measure the particle, the superposition collapses into a single definite state. What causes collapse? Nobody knows. Measurement? But what counts as measurement? Observation by a conscious being? Interaction with a larger system? The creation of information? We literally don't know what makes quantum mechanics work the way it does. The Copenhagen interpretation, championed by Niels Bohr, says we shouldn't ask what's really happening before measurement-only results of measurements are real. But this feels like giving up on understanding reality itself. The many worlds interpretation, proposed by Hugh Everett in 1957, says every quantum measurement causes the universe to split into parallel branches, with each possible outcome occurring in a different branch. The superposition never collapses. We just end up in one branch, while other versions of us experience other outcomes. This solves the measurement problem, but requires accepting the existence of an unimaginable number of parallel universes. Roger Penrose, one of the deepest thinkers about quantum gravity, suggests that gravity itself causes collapse when superpositions reach certain mass thresholds. But we can't test this The effects are too small to measure with current technology. Here's the mind-blowing part. Experiments in quantum mechanics keep getting weirder. In 2022, the Nobel Prize was awarded for experiments confirming that quantum entanglement, Einstein's spooky action at a distance, is real. When you measure one particle of an entangled pair, the other particle instantly takes on a correlated state, no matter how far apart they are. Not faster than light instantly. No signal travels between them. They're somehow connected in a way that transcends space. Einstein hated this and spent decades trying to prove it wrong. He failed. The universe genuinely contains connections that don't respect our notions of locality and separateness. Think of it like this. You have two coins, one in New York and one in Tokyo. In classical physics, each coin has a definite state heads or tails before you look. In quantum mechanics, neither coin has a state until you look at one of them. And the instant you do, the other coin simultaneously takes on the correlated state. Not because information traveled between them, but because they were never truly separate to begin with. The universe seems to be fundamentally non-local. Things that appear separate aren't really separate at the quantum level. Space itself might be an emergent property arising from quantum entanglement. As Juan Maldacina's work on the E=EPR correspondence suggests a connection between wormholes and quantum entanglement. But here's where we hit a limit. We can't scale quantum mechanics up to understand the world we see. The boundary between quantum and classical remains mysterious. Why don't we see macroscopic objects in superposition? When exactly does the quantum weirdness end and classical reality begin? We don't know. The theory works, but understanding what it means about reality seems to recede the closer we get. Let me tell you about something that keeps physicists awake at night. The universe shouldn't exist. Or more precisely, it shouldn't exist in a form capable of supporting complexity, structure, or life. Yet here we are. The fundamental constants of nature, the strength of gravity, the mass of the electron, the charge of the proton, the cosmological constant appear to be fine-tuned to absurd precision to allow the universe to be habitable. Let's start with the cosmological constant, which we talked about as dark energy. Its value is about y-122 in Planck units. That's a decimal point, followed by 121 zeros, and then a 1. But quantum field theory predicts it should be around 1 in Planck units, 10,122 times larger than observed. If the cosmological constant were just slightly larger, say, 10 to 120, instead of y122, the universe would have expanded so rapidly that no galaxies, stars, or planets could ever form. Everything would be ripped apart before structure could emerge. If it were negative, the universe would have collapsed back on itself in a big crunch within seconds of the Big Bang. The value we observe sits in an absurdly narrow range that allows both structure to form and the universe to exist long enough for that structure to become complex. The strong nuclear force that holds atomic nuclei together is another example. If it were 2% stronger, protons would stick together too efficiently, and hydrogen would be rare. No hydrogen means no water, and no stars like our sun. If it were 5% weaker, protons couldn't stick together at all, and we have no atoms heavier than hydrogen. The ratio of the electromagnetic force to the strong force is fine-tuned to within 1 part in 1040. If it were different, chemistry as we know it couldn't exist. Carbon, oxygen, nitrogen, the building blocks of life, couldn't form. Martin Rees, the British Astronomer Royal, identified 6 fundamental numbers that determine the universe's structure. If any one of them were different by even a small amount, the universe would be radically different, probably lifeless. Now, there are 3 ways physicists try to explain this. First, pure chance. Maybe we just got lucky, and we shouldn't be surprised, because if the constants were different, we wouldn't be here to observe them. This is called the anthropic principle, but it feels deeply unsatisfying, like explaining why you won the lottery by saying, well, someone had to win. Second, the multiverse. If there are infinite parallel universes with different physical constants, then some must have the right values for life, and obviously we find ourselves in one of those. This is the many worlds interpretation on steroids. But it's unfalsifiable. We can never observe other universes to confirm they exist. Third, some deeper theory we haven't discovered yet explains why the constants have the values they do. Maybe string theory's landscape of 10,500 possible universes contains some hidden mechanism that selects our particular set of constants. But we don't know what that mechanism would be. Here's what will blow your mind. The fine-tuning problem suggests that the universe is either incredibly lucky in a one-off way, one of infinitely many universes, most of which are dead, designed or selected by some principle we don't understand. Each option is philosophically disturbing. The universe is either a cosmic fluke, where in a multiverse we can never verify, or there's some teleological principle selecting for life-friendly universes. And this fine-tuning is a limit on physics. We can't explain why the constants have the values they do. We can only measure them and marvel at how improbably perfect they are. It's like discovering your house's address. Latitude, longitude, and altitude, when multiplied together, equal exactly the number of atoms in your body. The coincidence would be so extreme you'd suspect it meant something, but you'd have no way to prove it wasn't just chance. All right, I need you to prepare yourself, because what I'm about to tell you fundamentally challenges the notion of what space itself is. In the 1970s, Stephen Hawking discovered something shocking. Black holes aren't completely black. They emit radiation due to quantum effects near the event horizon, and eventually they evaporate completely. This creates a paradox. When matter falls into a black hole, it carries information about its quantum state. If the black hole evaporates, where does that information go? In quantum mechanics, information can never be destroyed. It's a fundamental law. But Hawking radiation appears to be random thermal radiation, carrying no information about what fell in. This is called the black hole information paradox, and it suggests that either quantum mechanics or general relativity must be wrong. Jacob Bekenstein proposed that black holes have entropy, a measure of disorder proportional to the surface area of their event horizon, not their volume. This is weird. Normal objects have entropy proportional to their volume. A bigger box can be arranged in more ways than a smaller box. But black holes seem to store all their information on their surface. This led Leonard Susskind and Gerard 't Hooft to propose the holographic principle. All the information contained in a volume of space can be represented as a theory on the boundary of that region. In other words, our three-dimensional reality might be a hologram projected from information encoded on a two-dimensional surface. Think of it like this. You think you're living in a 3D world, but actually, you're a character in a 2D movie being projected onto a 3D screen. All of your complexity, all your thoughts, all the physics of your world, it's actually encoded on a flat surface somewhere. And the third dimension is just how that information appears to you. Juan Maldacena made this concrete with the ADC-CFT correspondence, a mathematical equivalence between gravity in a volume of space and quantum field theory on the boundary. This isn't philosophy. It's rigorous mathematics showing that space-time itself might be emergent, not fundamental. Here's what will absolutely blow your mind. If the holographic principle is true, there's a maximum amount of information that can be contained in any region of space. This is the Bekenstein bound. For a sphere the size of Earth, the maximum information is about 1,069 bits. For the observable universe, it's about 10,122 bits. This means the universe has finite information content. Reality itself has a resolution limit. There are only so many possible states the universe can be in, and we're approaching a point where we might be able to calculate that number. But here's the disturbing implication. If reality is holographic and information is finite, then in principle, a sufficiently advanced civilization could create a simulation indistinguishable from our universe. The simulation hypothesis that we might be living in a computer simulation becomes not just possible, but potentially likely if civilizations tend to create many simulations of their past. Nick Bostrom's simulation argument goes like this. Either civilizations like ours go extinct before developing simulation technology, or they develop it but choose not to create simulations, or we're almost certainly living in a simulation because simulated beings vastly outnumber real ones. The holographic principle makes this disturbingly plausible because it suggests reality already operates like a computation information processing on a boundary, creating the appearance of three-dimensional space. We can't prove whether we're in a simulation or not. That's a fundamental limit on knowledge. If the simulation is perfect, there's no experiment that could detect it from the inside. Let's talk about time, because physics is suggesting that everything you think you know about past, present, and future is wrong. And this wrongness might be a fundamental feature of reality we can't escape. Einstein's special relativity, published in 1905, revealed that time is relative. Two observers moving at different speeds experience time differently. A clock on a fast-moving spaceship runs slower than a clock on Earth. This isn't an illusion. It's real. Astronauts on the International Space Station age slightly slower than people on the ground. But here's the deeper implication. Special relativity implies that now isn't absolute. Events that appear simultaneous to one observer happen at different times for another observer, moving at a different speed. There's no universal present moment. Your now and my now are different if we're in relative motion. This leads to the block universe interpretation. Imagine the entire history of the universe, past, present, and future existing as a four-dimensional block. From outside this block, every moment exists equally. The Big Bang and the heat death of the universe billions of years from now are both just different slices of the block, all existing simultaneously. Think of it like a movie on a DVD. Every frame exists on the disc simultaneously, but when you watch it, you experience the frames sequentially. The block universe suggests our experience of time flowing is like watching that movie's subjective experience of an objective static structure. This view is supported by general relativity. Einstein's equations describe spacetime as a geometric structure where past, present, and future all exist. The equations don't pick out any moment as special. To the equations, all times are equal. But if the block universe is correct, what about free will? If the future already exists in the same way the past does, how can our choices matter? Are we just experiencing the playing out of events that were always going to happen? Carlo Rovelli, one of the pioneers of loop quantum gravity, suggests time might not be fundamental at all. At the deepest level of reality, the quantum level, time might not exist. The flow of time might emerge from thermodynamics, the tendency of systems to move from order to disorder. We experience time flowing forward because entropy increases, not because time itself is fundamental. Here's what will blow your mind. There are solutions to Einstein's equations that allow for closed time-like curves paths through spacetime that loop back on themselves, allowing travel to the past. Kurt Dell, famous for his incompleteness theorems in mathematics, discovered one such solution in 1949. If you traveled along a closed time-like curve, you could meet your younger self. Do these exist in our universe? Probably not. They require exotic matter with negative energy, and they seem to lead to paradoxes. But the fact that the mathematics allows them suggests that our understanding of causality and time is incomplete. Quantum mechanics adds another layer of strangeness. The quantum eraser experiments show that future measurements can affect what happened in the past. If you do an experiment where a photon takes one of two paths, you can delay the measurement of which path it took. When you finally measure, the photon's behavior changes retroactively. It behaves as if it knew what measurement you are going to make in the future. This isn't time travel, but it suggests that quantum systems don't respect our intuitive notion of causality. The past isn't fixed until the future measurement is made. We're approaching a limit where our intuitions about time completely break down. Past, present, and future might all exist simultaneously. Time might not be fundamental. Causality might be negotiable at quantum scales. And there's no experiment we can do to experience time differently than we do, because we're embedded in time. We can't step outside it to see what it really is. Now we're entering dangerous territory. We need to talk about consciousness because, against all odds and against the preferences of most physicists, consciousness keeps showing up at the boundaries of what physics can explain. The measurement problem in quantum mechanics explicitly involves observation. Before measurement, superposition. After measurement, definite state. But what counts as measurement? Does it require a conscious observer? The founders of quantum mechanics, Bohr, Heisenberg, von Neumann, took consciousness seriously as part of the measurement process. Eugene Wigner even proposed that consciousness causes wave function collapse. His friend's thought experiment imagines a person performing a quantum measurement inside a sealed room while Wigner is outside. From the friend's perspective, the measurement has occurred and the result is definite. From Wigner's perspective, until he opens the room, his friend and the quantum system are in superposition. Does the friend's consciousness collapse the wave function, or does Wigner's? Most physicists today are uncomfortable with consciousness playing a fundamental role. They prefer explanations involving decoherence, where interaction with the environment causes superpositions to become correlated with the environment, creating the appearance of collapse without consciousness. But the problem won't go away. Roger Penrose and Stuart Hameroff proposed that consciousness arises from quantum computations in microtubules inside neurons, and that consciousness is linked to gravitational effects on quantum superpositions. This is controversial and not widely accepted, but it suggests that consciousness might be where quantum mechanics and gravity meet, exactly where physics breaks down. Here's an even stranger possibility. Integrated information theory, developed by Giulio Tononi, suggests that consciousness is a fundamental property of systems that integrate information. The more integrated information a system processes, the more conscious it is. Under this theory, consciousness isn't limited to brains. Any system that integrates information has some degree of consciousness. If this is true, consciousness isn't separate from physics. It's a quantifiable physical property. But we can't measure integrated information directly except in very simple systems. Consciousness might be real, fundamental, and quantifiable, yet largely inaccessible to objective measurement. Think of it like this. You know for certain that you're conscious. You experience qualia, the subjective feeling of redness, the taste of coffee, the sensation of pain. But you can't prove to anyone else that you're conscious. No brain scan can detect qualia directly. Consciousness might be the one thing that's absolutely real to you, but fundamentally private, unmeasurable, and locked inside your subjective experience. John Wheeler, toward the end of his life, proposed a participatory universe where observers don't just measure reality, but participate in bringing it into existence through their observations. In his view, the universe is a self-excited circuit observing itself into existence. This sounds crazy until you remember the delayed choice quantum eraser experiments, where measurements in the present seem to affect what happened in the past. Wheeler suggested that observers in the present might be reaching back through time to solidify what was previously probabilistic, creating a universe where observation and reality are fundamentally intertwined. Here's what will blow your mind. If consciousness is necessary for wave function collapse, and if the many worlds interpretation is wrong, then every conscious observer is somehow collapsing superpositions constantly, transforming probabilistic quantum mush into the definite classical reality we experience. Your consciousness might be actively creating reality moment by moment. But this is a limit we can't overcome. We can't do experiments on consciousness from outside consciousness. We're trapped inside our subjective experience, unable to objectively study the thing that makes objectivity possible in the first place. Okay, let's take a breath and make this personal, because what we've been discussing isn't just abstract physics. It's about you and your place in this universe that's revealing itself to be far stranger than anyone imagined. You exist at an extraordinary moment in cosmic history. Think about that. For 13.8 billion years, the universe evolved, stars formed, galaxies collided, planets coalesced. For 4 billion years on Earth, life evolved from single cells to complex organisms. For 200,000 years, humans existed but couldn't ask these questions. For 400 years, we've had modern science. And now, in your lifetime, this brief flicker of time, we're hitting the fundamental limits of what reality will allow us to know. You're living through physics's end game. But here's the beautiful part. Those limits aren't failures, they're revelations. The Planck length reveals that space is quantized, pixelated, granular. The universe has resolution. The energy desert between what we can probe and where the answers. Hyde tells us that reality operates on scales completely divorced from human experience. The measurement problem shows that observation and reality are entangled in ways we're only beginning to understand. Every limit we've discussed is the universe telling us something profound about its nature. The universe isn't withholding information despite us. It's showing us that reality at its deepest level operates on principles so far removed from everyday experience that even our best theories break down. And you're part of that reality. Your body is made of atoms forged in stellar cores. The calcium in your bones, the iron in your blood, the oxygen you breathe, all created in the heart of dying stars billions of years ago. You're literally made of stardust, arranged in a pattern complex enough to contemplate its own existence. Your brain contains roughly 86 billion neurons, each connected to thousands of others, creating a network of trillions of connections. The information processing capacity of your brain approaches the theoretical limits for a system of its size and energy consumption. You're a nearly optimal information processing machine operating at the edge of what biology can achieve. When you observe something, you're participating in the collapse of quantum superpositions, transforming the probabilistic into the definite. Whether or not consciousness is required for collapse, you are an observer. And observers shape reality in quantum mechanics. You're not just in the universe. You're helping determine what's real. Here's what I need you to understand. The limits of physics aren't limits on you. They're the boundaries of a playground so vast that we've been exploring for centuries and have only now begun to reach the edges. And those edges? They're where the most interesting questions live. You might never know what happens inside a black hole's singularity. You might never discover what dark matter is. You might never probe the Planck scale. But you live in a universe where those mysteries exist, where reality is strange enough to have event horizons and quantum foam and parallel universes. That's incredible. Most people throughout history lived and died never knowing that galaxies existed, never suspecting that time could be relative, never imagining that particles could be entangled across space. You know these things. You can look at the night sky and comprehend, at least partially, what you're seeing: photons that traveled for millions of years, carrying information about stars that might already be dead. You have a frontal cortex capable of abstract reasoning. You can hold contradictory ideas in mind and examine them. You can feel awe. Awe is a cognitive emotional response to something vast that challenges your understanding, and you're capable of feeling it, specifically because your brain evolved to model the world and recognize when that model is insufficient. The limits of physics should inspire awe, not despair. They mark the boundaries where reality becomes so strange, so removed from everyday experience, that even mathematics struggles to describe it. And you get to witness this. You get to live in the moment where we're glimpsing those boundaries. So if we're approaching fundamental limits, what happens to physics as a discipline? What comes after we've hit walls we can't climb? The history of science suggests that when we hit limits, we don't stop, we change direction. When physicists couldn't build bigger telescopes to see farther, they invented new methods: gravitational wave detection, neutrino astronomy, using the entire Earth as a detector. When particle physics couldn't build larger colliders, they started using precision measurements to search for tiny deviations from the standard model. LIGO, the Laser Interferometer Gravitational Wave Observatory, detected gravitational waves in 2015 ripples in spacetime from colliding black holes 1.3 billion light-years away. These detectors didn't see light. They measured distortions in space itself, smaller than the width of a proton. This opened an entirely new way of observing the universe. The Event Horizon Telescope captured the first image of a black hole in 2019 by turning the entire Earth into a radio telescope, combining data from dishes across the planet. When you can't build a telescope the size you need, you coordinate many telescopes to act as one. Quantum computers might help us simulate physical systems too complex for classical computers. If we can't build a particle collider large enough to test string theory, maybe we can simulate the quantum field theories that emerge from string theory and compare them to precision measurements. Machine learning is already being used to find patterns in particle physics data that humans miss. AI might discover symmetries or relationships in our theories that point toward deeper understanding, even when we can't directly test them. But here's the unsettling possibility. We might be entering an era of post-empirical physics theories that are mathematically sophisticated and internally consistent. But that can't be tested experimentally because they make predictions at inaccessible energy scales or distance scales. String theory is already arguably post-empirical. Loop quantum gravity makes predictions at the Planck scale we can't test. Many multiverse theories are unfalsifiable by definition. If other universes are truly inaccessible, no experiment can confirm they exist. Richard Dodd argues that we might need new criteria for theory confirmation beyond experimental testing. Maybe mathematical consistency, explanatory power, and uniqueness, if a theory is the only one that works, should count as evidence even without direct empirical confirmation. But many physicists resist this. Lee Smolin argues that abandoning empirical testability means abandoning science for philosophy or mathematics. The philosopher of science Karl Popper said theories must be falsifiable to be scientific. If string theory can explain any observation by adjusting its parameters, it's not making genuine predictions and isn't science. Here's what will blow your mind. We might have to accept that some questions about reality are permanently beyond our ability to answer empirically. Not because we're not smart enough, or because we don't have good enough technology, but because the universe's structure prevents those answers from being accessible. Think of it like this. Imagine you're a character in a video game trying to understand the computer running the game. You can study the rules of the game world exhaustively, but you'll never directly observe the CPU, the memory, the programming language. Those exist at a level fundamentally inaccessible from inside the game. Maybe we're in a similar position. Certain aspects of reality might be fundamentally outside our light cone, below our resolution limit, above our energy ceiling. But this doesn't mean physics is dead. It means physics is transforming. We'll focus on precision measurements, on understanding complex emergent phenomena, on quantum information theory, on applying what we know to solve practical problems. Quantum computing, quantum cryptography, advances in materials science, better understanding of biological systems. These all emerge from fundamental physics, even if we're not discovering new fundamental particles. The golden age of finding new fundamental layers might be ending, but the golden age of understanding how complexity emerges from the fundamentals we've discovered, that's just beginning. We need to return to fine-tuning, but this time, I want you to really feel the weight of what it means for you personally. Brandon Carter introduced the anthropic principle in 1973. In its weak form, it simply says, we observe the universe to have properties compatible with our existence, Because if it were different, we wouldn't be here to observe it. This seems trivial, of course. We find ourselves in a universe that allows us to exist. But the strong anthropic principle suggests something deeper. The universe must have properties that allow consciousness to develop at some point in its history. This implies that consciousness is somehow built into the structure of reality, that observers are necessary for the universe to be fully realized. John Wheeler took this further with his participatory anthropic principle. Observers are necessary to bring the universe into existence. In quantum mechanics, the universe exists in superposition until observed. Wheeler suggested that conscious observers in the present might be collapsing the wave function of the entire history of the universe retroactively. This creates a bootstrap paradox. The universe needed to exist long enough to produce observers, but observers are needed to collapse the universe into a definite state. The universe and its observers bring each other into existence in a cosmic feedback loop. Here's where it gets personal. You are one of those observers. Your existence and your observations are part of the mechanism by which reality becomes definite. You're not just in the universe. You're part of the process that makes the universe real. Let me put it another way. Roughly 1,080 atoms exist in the observable universe. The number of ways to arrange those atoms is staggeringly larger 10 to the power of 1,080 or more. Almost all possible arrangements are boring random distributions of particles in empty space. The number of arrangements that produce stars is tiny. The number that produce planets is tinier still. The number that produce life is vanishingly small. The number that produce intelligent observers is almost infinitesimal. Yet here you are, an arrangement of atoms so improbable that across the observable universe, intelligent life might be extraordinarily rare. You're a pattern of matter that can contemplate its own existence, understand quantum mechanics, feel love and fear, create art, ask why. If the cosmological constant were slightly different, you wouldn't exist. The universe would have expanded too quickly for structure to form, or collapse too soon. If the strong nuclear force were 5% weaker, carbon wouldn't form in stellar cores, and you wouldn't exist. If electromagnetism were slightly stronger, chemistry would be too unstable for life, and you wouldn't exist. You exist because the fundamental constants are exactly what they need to be. This is either an extraordinary coincidence, or you're in a universe selected from many for life friendliness, or something about the universe's structure requires the constants to have life-permitting values. But here's the beautiful paradox. The anthropic principle explains why the universe appears fine-tuned by pointing out that we couldn't observe it any other way. But this explanation only works if observers like you exist. You're simultaneously the thing being explained and part of the explanation. Think of it like this. The universe produces observers, and observers give meaning to the universe. Without galaxies, stars, planets, and life, the universe would be just quantum fields oscillating in empty space. No one to observe it, no one to understand it, no meaning or purpose. Consciousness transforms the universe from a sterile mathematical structure into something experienced, felt, contemplated. You are how the universe knows itself. Carl Sagan said this poetically. We are a way for the cosmos to know itself. But it's not just poetry. If consciousness is necessary for wave function collapse, or if observation is required to transform quantum potentiality into classical actuality, then observers are literally what makes reality real. And if the universe is fine-tuned for observers, then in some deep sense, the universe is structured to produce you. Not you specifically, but conscious observers in general. You're not an accident. You're an inevitability, given the right constants. And somehow, against all odds, we have the right constants. Let's talk about something that physicists often don't like to admit. Even if we knew all the fundamental laws perfectly, we still couldn't predict most of what happens in the universe because of complexity. Reductionism, the idea that complex things can be understood by breaking them down into simpler components, has been incredibly successful. Chemistry reduces to physics. Molecules reduce to atoms. Atoms reduce to particles. This reductionist program has driven physics for centuries. But there's a problem. Knowing the parts doesn't always let you predict the whole. This is the principle of emergence. Complex systems exhibit properties that their components don't have, and that can't be easily predicted from the components alone. Philip Anderson, a Nobel Prize-winning physicist, wrote a famous paper in 1972 called "More is Different," arguing that each level of complexity requires its own concepts and principles. You can't derive biology from particle physics, not because the particles behave differently in biological systems, but because biological systems are so complex that new organizing principles emerge. Think of it like this. You can know every rule of chess perfectly, how each piece moves, how the game starts and ends, but that doesn't let you predict who will win a game between two grandmasters. The complexity of possible moves creates an emergent space of strategy that can't be reduced to the rules. Consciousness is perhaps the most dramatic example. Your brain is made of neurons, which are made of molecules, which are made of atoms, which are made of particles. We understand how particles work. We understand chemistry. We understand how neurons fire. But we don't understand how consciousness emerges from all of this. The hard problem of consciousness, why physical processes in the brain create subjective experience, remains unsolved. Some philosophers argue consciousness can't be reduced to physics because qualia subjective experience is fundamentally different from physical processes. Others argue we just don't understand emergence well enough yet, and consciousness will eventually be explained. But here's the disturbing possibility. Emergence might be a fundamental limit on knowledge. Systems above a certain complexity threshold might be irreducible. You'd have to simulate the entire system to predict its behavior, and the simulation would be as complex as the system itself. No shortcuts, no simplified models, no elegant equations. The three-body problem in classical mechanics is a simple example. Two bodies orbiting each other? Easy, we have exact solutions. Add a third body, and the system becomes chaotic. No general solution exists. You have to simulate it numerically, step by step, to see what happens. Turbulence in fluids is another example. We have the Navier-Stokes equations describing fluid flow, but we can't solve them for turbulent flows. Turbulence creates patterns at all scales. Large eddies contain smaller eddies, which contain smaller eddies, fractally, down to molecular scales. You need to track everything to predict anything. Climate is an emergent complex system. We understand the physics of atmospheric gases, ocean currents, ice sheets. But predicting long-term climate requires tracking so many interacting components that small uncertainties grow exponentially. This is chaos extreme sensitivity to initial conditions. Life itself is emergent. You can describe all the chemical reactions in a cell, but that doesn't capture what it means to be alive. Living systems self-organize, self-repair, reproduce, evolve. These properties emerge from chemistry, but aren't obvious from studying molecules in isolation. Economies are emergent. You can study individual transactions, but predicting market behavior requires understanding emergent properties like bubbles, crashes, feedback loops, and network effects that aren't reducible to individual decisions. Here's what will blow your mind. Emergence suggests that even in a purely deterministic universe, where everything is governed by known laws, the universe is still fundamentally unpredictable because complexity generates novelty. And if the universe is quantum mechanical fundamentally, probabilistic then, unpredictability is built in at the ground floor. The future is not determined by the past, even in principle. Laplace's demon, the idea that a sufficiently powerful intelligence could predict the entire future from perfect knowledge of the present, is wrong. Heisenberg uncertainty prevents perfect knowledge. Quantum measurement creates genuine randomness, and chaos amplifies tiny quantum fluctuations into macroscopic unpredictability. This is a limit on knowledge. Even if we knew all the laws, we couldn't predict everything. The universe is too complex, too chaotic, too quantum. Reality generates surprises. All right, we need to confront something heavy. Learning about the limits of physics can be existentially unsettling. We live in a culture that celebrates progress, that assumes tomorrow will bring new discoveries, that believes no question is unanswerable, given enough time and effort. But what we've been discussing suggests otherwise. Some questions might not have answers we can access. Some mysteries might be permanent. The arc of scientific progress might not bend toward complete understanding. It might asymptotically approach a boundary beyond which we cannot pass. How should you feel about this? Let me tell you how I think about it. The limits of physics aren't depressing, they're liberating. They tell us that reality is richer, stranger, and more complex than our theories. The universe isn't a solved puzzle. It's an inexhaustible source of wonder. Think about music. We understand the physics of sound waves, perfectly frequency, amplitude, resonance, harmonics. We can analyze any song and describe exactly what's happening acoustically. Does that make music less beautiful? Does understanding sound waves reduce the emotional power of a symphony? Of course not. The physics is just one layer. The meaning, the emotion, the artistic expression, these emerge from the physics but aren't reducible to it. The same is true for reality itself. Physics describes the substrate, the rules, the mechanisms. But meaning, purpose, beauty, love, consciousness, these emerge from the physics but transcend it. You don't need a complete theory of quantum gravity to live a meaningful life. You don't need to understand dark matter to experience awe at the night sky. The limits of physics create space for mystery, and mystery is essential to the human experience. If we understood everything, if every question had a definite answer, the universe would be smaller, more mechanical, less wondrous. Friedrich Nietzsche said that if we explain all the mystery out of life, we make it unbearable. The mystery is part of what makes existence profound. And physics, far from eliminating mystery, has revealed depths of mystery our ancestors couldn't have imagined. Here's another way to think about it. Physics has given us the gift of better questions. 400 years ago, people didn't know to ask about space-time curvature, quantum entanglement, dark energy, or black hole information. We've progressed not just in answers, but in the sophistication of our questions. We're asking questions at the edge of what's knowable, and that's extraordinary. You live at a time when we understand enough to see the boundaries, but not enough to cross them. Future generations might live entirely on one side or the other, either accepting the boundaries as permanent, or having somehow transcended them through insights we can't currently imagine. But you're here at the transition, watching physics grapple with its own limits in real time. That makes you privileged, not deprived. Moreover, the limits of fundamental physics don't limit what you can do. Engineering, medicine, computer science, materials science. These fields have decades or centuries of development ahead, even if we never discover another fundamental particle. The applications of known physics are far from exhausted. And personally, the limits of physics don't limit your agency or meaning. Whether or not you have free will in a deterministic universe, you experience making choices. Whether or not consciousness is reducible to neurons, you experience being conscious. Whether or not you're in a simulation, your experiences feel real to you and matter to you. The philosopher Thomas Nagel pointed out that even if consciousness is just neurons firing, it's still something to be conscious. The subjective experience is real and significant regardless of the underlying mechanism. Your life has meaning because you experience it as meaningful, and no amount of reductionism changes that. Let me ask you, if someone proved tomorrow that the universe is deterministic and free will is an illusion, would you stop making decisions? If someone proved we're in a simulation, would your relationships stop mattering? If someone proved consciousness is just computation, would you stop feeling emotions? Of course not. Because the lived experience is what matters, and that's immune to reductionist explanations. You exist at the level of human experience, where meaning lives, regardless of what's happening at the Planck scale. So where does physics go from here? If we're at the limits, what happens to the field? One possibility, we're not actually at the limits. History is full of physicists declaring that everything important has been discovered, only to be blindsided by revolutions. Maybe there's a third major revolution, waiting something beyond quantum mechanics and relativity that overturns everything we think we know. Some candidates, quantum gravity obviously, but maybe also a theory of consciousness that integrates it into physics. Maybe the discovery of dark matter reveals a whole new sector of particles and forces we're currently blind to. Maybe we discover that the constants of nature aren't constant, they evolve or vary across space. Maybe we detect signals from other universes in the multiverse or evidence of a simulated reality. Or maybe none of those things happen, and we enter a long period of consolidation and application rather than revolution. This has happened before. After Newton, physics spent 200 years working out the implications of his laws before needing a new revolution. After Maxwell unified electromagnetism, there were decades of development before quantum mechanics became necessary. We might be in for a century of working out the implications of the Standard Model and general relativity, finding precision tests, discovering emergent phenomena, building quantum technologies, even if no new fundamental physics is found. Or maybe physics splits. One branch becomes increasingly mathematical and post-empirical, working on string theory and quantum gravity and multiverse cosmology without experimental tests, operating more like mathematics or philosophy. Another branch stays empirical, working on condensed matter physics, quantum computing, materials science, biophysics applying known physics to complex systems. Both would be valuable. The post-empirical branch would push the boundaries of human thought, even without experiments. The empirical branch would solve practical problems and advance technology, even without new fundamental laws. But here's a more radical possibility. Maybe physics, as currently conceived, is approaching its end, and the next revolution will be so profound that it doesn't look like physics at all. It might involve consciousness, information, or computation as fundamental rather than derived. It might reject reductionism entirely and embrace holism or emergence as the primary organizing principle. Physicist Max Tegmark proposes that reality is literally mathematics, not described by mathematics, but made of mathematics. If true, physics is really just the study of which mathematical structures are instantiated in our universe. The next revolution might be figuring out why this particular mathematical structure and not others. Or maybe the next revolution is technological rather than conceptual. Quantum computers might let us simulate physical systems currently inaccessible. I might discover patterns we can't see and generate theories we wouldn't have thought of. Brain-computer interfaces might extend our cognitive abilities enough to grasp concepts currently beyond human comprehension. There's a hypothesis called the transcension hypothesis that suggests advanced civilizations don't expand outward into space, but inward into computational substrate, creating smaller, denser, faster, more efficient systems. Maybe the future of physics is miniaturization, creating technologies that operate at quantum or even Planck scales, accessing physics we currently can only theorize about. Or maybe we're approaching something like the omega point concept by physicist Frank Tipler, where computation accelerates without bound as the universe contracts, allowing infinite information processing in finite time. Far future civilizations might simulate all possible physical theories and determine which is true through exhaustive computation rather than experiment. Here's what will blow your mind. The end of one kind of physics might be the beginning of another. When we can't go deeper into fundamental particles, we go wider into complexity. When we can't build bigger colliders, we build more precise detectors. When we can't reach higher energies, we simulate quantum systems. When we can't test string theory directly, we look for indirect signatures in precision measurements of the standard model. Physics doesn't end, it transforms. And you're witnessing that transformation. We've traveled together through 180 minutes of the deepest, most challenging ideas in modern physics. You've learned about Planck limits in energy deserts, quantum measurement problems and holographic principles, fine-tuning and emergent complexity. You've confronted the limits of what can be known and the boundaries reality has drawn around human understanding. Now I want to bring this home with one final idea that connects everything. You matter. Not in some vague, feel-good way. I mean, you matter in a precise, physical, undeniable sense. Let's start with the obvious. You're here. In a universe with a cosmological constant that could have been any value, but happens to be exactly right for structure formation, you exist. In a universe with fundamental constants that could have made chemistry impossible or carbon unstable, you're made of complex molecules. In a universe that's 13.8 billion years old, you're alive during a brief window when stars burn, when galaxies exist, when planets harbor life. The universe had to be exactly what it is for you to be here. And you are here. That's not nothing. That's extraordinary. But there's more. Your brain, this 3-pound mass of neurons inside your skull, is one of the most complex structures in the known universe. With roughly 86 billion neurons and trillions of synaptic connections, your brain approaches the upper bound of what's possible for a biological structure, operating on chemical energy in Earth's gravity well. Every thought you have involves thousands or millions of neurons firing in coordinated patterns, quantum tunneling of ions across membranes, chemical signals cascading between cells. You're a quantum classical hybrid system operating at multiple scales simultaneously molecular, cellular, systemic, creating consciousness through mechanisms we still barely understand. When you observe the universe, you're not a passive receiver of information. You're an active participant. In quantum mechanics, observation changes the system. Your measurements collapse superpositions. Your choices affect outcomes in genuinely probabilistic systems. If the participatory anthropic principle is right, you're helping bring reality into existence through the act of observation. And even if that's too radical, even if observation doesn't literally collapse wave functions, you're still a remarkably complex pattern recognition and information processing system that transforms raw sensory data into subjective experience, abstract thought, and understanding. You can comprehend concepts far removed from daily experience. You can understand that space-time is curved even though you can't visualize four-dimensional geometry. You can grasp quantum superposition even though it violates classical intuition. You can contemplate the Big Bang, black holes, and the heat death of the universe billions of years in the future. This cognitive ability, this capacity for abstract reasoning about domains far removed from ancestral environments, is almost certainly rare in the universe. Most life, if it exists elsewhere, is probably simple bacteria, algae, maybe complex animals. But intelligence capable of doing science? That might be extraordinarily rare, which means you personally, with your human brain, might be one of a very small number of conscious entities in the observable universe currently capable of understanding physics at this level. You're part of an elite group, not because you're special compared to other humans, but because humans are special compared to most other possible arrangements of matter. You're a way for the universe to understand itself, and that role is crucial. If consciousness is required for wave function collapse, then before conscious observers existed, the universe was in a grand superposition of all possible states. The emergence of observers like you transformed the universe from potential to actual. Even if consciousness isn't required for collapse, you're still giving the universe meaning. A universe with no observers is just fields and particles evolving according to equations. It doesn't mean anything because meaning requires minds to interpret, contextualize, care. You do that. Your existence transforms the universe from a mechanism into something experienced, contemplated, appreciated. When you look at a sunset and feel awe, you're not just passively receiving photons. You're a complex system that evolution shaped to respond emotionally to specific stimuli. And that emotion, that qualia of awe's something real, something that exists in the universe because you exist. When you love someone, neurons fire in patterns unique to you, creating an emotional state that's never been exactly duplicated in the history of the universe and never will be. Your specific instance of love is unique, irreplaceable, cosmically singular. When you create something, write a story, compose music, solve a problem, you're adding information to the universe. You're creating patterns that didn't exist before. In an information theoretic sense, you're increasing the complexity and richness of reality. You exist in that space between knowledge and mystery. You understand enough to see the boundaries, but not enough to dissolve the mystery. And that's the perfect place to be. Too little knowledge, and the universe seems arbitrary and incomprehensible. Too much knowledge, if such a thing were possible, and the universe might seem mechanical and devoid of wonder. You're in the sweet spot. You can understand quantum mechanics without losing the sense of its strangeness. You can comprehend cosmological scales without losing the feeling of insignificance that creates perspective. You can learn about determinism and probability without losing your sense of agency. The universe is vast beyond comprehension, 93 billion light years across in the observable portion alone, possibly infinite beyond that. You're a tiny speck on a tiny planet orbiting an average star in an unremarkable galaxy in an ordinary region of space.